Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have any problem today. We want to simplify Newton's second law. Sir Isaac Newton, is that his name? So what's the main idea of Newton's theory? His basic big idea is that forces cause acceleration. We're actually introducing a new idea, the idea of something called a force. By the way, that's opposed to velocities because here's the deal. No force is needed to keep an object moving at constant velocity. Now, what does that mean? In the first law, we said that an object is at rest, it stays at rest. But an object that's in motion stays in motion. That's Newton's first law. So we talk about his second law. The deal is how do we change its movement? We have to apply a force, because if it's already moving, it's going to keep moving. It's strange, right? So in fact, the acceleration, okay, this is important, is proportional. Now we're getting a little mathy here. Ooh, that word, proportional to the total force. All right, here, fancy little terminology here. This is counterintuitive, though, to most. This can be easily demonstrated. Imagine a mass on a table connected by a string to a mass hanging off the edge of a table. So we've got like a cart, and then we've got a pulley, and this has got a weight. He's right here. Okay, what happens? What happens when a mass hanging off the edge of the table is doubled? Well, tell you what. Why don't we investigate that right now? So as we're talking about Newton's second law, I've got a cart right here attached by a string, and then we've got a weight right here attached to a pulley, right? And we're going to watch and see what happens when we release it. So here I have my cart, and as I let go, we have a mass at the end. As I let go, it accelerates. Now what I want to do is I want to increase the weight of the cart by putting some more weight on the cart, and now let's see what happens. You see how it accelerates much slower. So the heavier the cart, the bigger the mass, the less the acceleration. The greater the force, as represented by the tip of this, the greater the acceleration. And obviously if I were to take this out, let's take the entire weight, big weight out of this. Watch this, what's going to happen. So I have a super light cart. Watch what happens. It accelerates very rapidly towards the floor. So that's Newton's law in action to understand how this all works. Let's go back to the screen. Wasn't that like super cool? Now you get an idea that when we talk about this, it's not that difficult. So let's derive Newton's law. What we're saying here is the acceleration, now acceleration is a vector, right? We learned about the vectors before, is proportional, that's the fancy proportional, to the net force. All right? But it's also proportional, if you think about it, because we changed the mass, right? So if we increase the force, it's proportional to 1 over the mass. Now this is the mass of the cart, right? So when we made the cart less massive, it accelerated more rapidly, correct? So the smaller the mass, the bigger the acceleration. And the greater the force, the greater the acceleration. So if we have these two terms, A is both proportional to the force and also proportional to 1 over the mass, we can essentially say A, I'll do this algebraically, is proportional to the force, now technically the force net, let's get that down, divided by the mass. And the force is a vector. That's, folks, that's Newton's second law. Now let's just briefly talk about this F. What the heck is a force? A force is measured, if you think about it. So actually, let's sort of rewrite this. The force is measured in a unit called a Newton. This can be rewritten, if you think about it, as F net, this is the most common way it's written, by the way, equals the mass times the acceleration. Force is mass times acceleration. FMA, F equals ma. And what's the unit on force? Well, mass in the SI system is a kilogram. Acceleration, as you recall, is a meter per second squared. So a kilogram meter per second squared, that's the unit on force. Now we simplify this, and guess what we call this? I'll bet you're not surprised. The unit on a force, this unit, which is kilogram meter per second squared, is an N, capital N, which says a Newton's second law, right? So that comes from, of course, Sir Isaac Newton. So now what I want you to do is I want you to just draw some diagrams that would help you to understand the ideas of the proportionality of the forces. So what I'm thinking about is I'll do one. Let's see. If I've got some object, boom, with some mass, okay, and I apply a force to it, then it's going to have some kind of acceleration. All right, but see if you could figure this out. What if I have a tiny mass with the same force? What would happen to its acceleration? Right, same force, like say it's 10 newtons here or something, and 10 newtons. Or what if I have a really, really big mass, right? Big mass, and apply the same force. What's going to happen to the acceleration? Kind of draw that graphically in the box provided. Hopefully what you did is what you saw that is right here. When you have a big a force on a smaller object, the acceleration went fast. And here, because it's the same force, let's say it's 10 newtons, but it's on a bigger mass, the acceleration is little, sort of illustrated by these arrows. So let's do some like real example. Okay, if we've got a 5 kilogram wooden crate, diagram, experiences a 6.1 Newton force, calculate the crate's acceleration. So if this is 5.7 kilograms, and it's a force 6.1 newtons to the west, this is to the west, hello, and this is 6.1 newtons, what is the acceleration? All right, so 5.7, 6.1, what am I going to do? So acceleration, as you recall, is equal to the F net. Now again, these are vectors over the mass. Well, I know the force, that's 6.1 newtons divided by 5.7 kilograms. And I get my calculator out, and I get the acceleration to be equal to 1.07 meters per second squared. That's the units on acceleration, right? And that'll be to the west. All right? So that is the acceleration of this crate. So that's pretty easy, isn't it? Now, you're going to say, oh, I can do that. But when we start talking about if you will, east, west, north, south, we can run into some problems. It leads us to what we call free body diagrams, and it all starts with a picture. So here, let's try and draw this one. We've got a raft, all right, so we've got the raft. I'm going to write the word raft. Box on the raft. Now let's see, there is an upward buoyant force equal in magnitude to the force of gravity of 1,225 newtons down. I'm going to draw this. So this is 1,225 newtons up. That's the buoyant force. And then the force of gravity is 1,225 newtons down. That's the force of gravity. There's also a force of 150 newtons east from strong winds. So I'm going to draw that, and that's 150 newtons. This is the wind. And that's to the east, right? And you have a 215 Newton force, and it's, by the way, also east from the current. Draw the free body diagram for the raft, and then find F net and A. Now notice, this is kind of nice as we don't have angles and junk, but do you realize what's going on here is that these things are canceling? Let's take a few notes and then come back to this problem here in a second. Some things to note. Only draw the forces that are acting upon the object. We do not include forces the object is exerting on other objects, like the raft pushing on the water, which it does. We'll talk more about that. Multiple forces in the same direction are drawn next to each other. If a force is acting down on an object, we draw this force below the shape. This is just how we draw these free body diagrams. Force vectors always point away from an object. And the length of the force vectors are relative to the strength. That is, that the longer ones have longer vectors. And I just drew those, here. Notice how I put these in the same direction, up, down, etc. So we're usually, I should say, we're going to have up, down, east, west, left, right, directions, but sometimes it's not going to be the case. So let's go back and let's see if we can solve this problem. So it'll be on your next page. You're going to ask the question, what is the net of the equation from this example here? I'm just going to do it right here. Do you realize that the up and down, what do? They cancel, because one's up, one's down, so they cancel. So what we have is we have a easterly flow of 150 plus 215. So I'm going to say F net to the east is going to be 150 newtons plus 215 newtons equals 365 newtons to the east. Right? And what we're going to do is, I guess the thing we're going to say is, actually I should have said this. What's the big equation? It's in your packet. The overall equation is F net is equal to F1 plus F2 plus F3. Add up all the forces. Vectorially add them all up. And by the way, I'm making a note that I already added or canceled out the up and the down force. And this is the overall net force right here to the east. Now the question wasn't what's the net force, but what's the overall acceleration. And so we can say acceleration, if you recall, is equal to F net divided by the mass. Well, the F net is 365 newtons east divided by the overall mass. And the overall mass, if you recall from the problem, was 125 kilograms. So we take 365 divided by 125. The acceleration is equal to 2.92 meters per second to the east. Make sense? All right. Now let's make the problem the hardest you can see in this one. All right. Now we have a more complex problem. We have a 19 kilogram sled. This has 19 kilograms. 19, there we go. And let's talk about this. The younger sibling pulls with a force of 17 newtons, 15 degrees north of east. So this is east. 15 degrees north of east. This is 15 degrees. And he's pulling with 17 newtons. Okay? And the younger sibling pulls, and then the elder is 21, and he's going to be 12 degrees east of south, or south of east. Hello, my thing's going weird. This is 12 degrees, and he's going to be a little harder, and he's going to be 21 newtons. Basically, the question is, what is the overall net force? Now we've gotten to delay the sine, cosine. So let's work with the first vector, the 17 degrees. So I can say that F1y is equal to sine 15. So this is 15 degrees. We're going to play SOHCAHTOA games. So this is the y direction, right? What's going to be the y? It's going to be whatever this is. It's opposite over hypotenuse. So sine of Fy. So this is actually, I'll do it this. It's not equal to, but I'm just find the y. Over 17. But it's sine of 15 degrees, right? This equals 4.4 newtons, okay? Let's do the y for this 21 degrees. So F2y is equal to sine, so it'd be 21 times sine of 12 degrees. Okay, so now as a note, this one's to the north, right? And this one's to the south because, right, the one is pushing up and one is pushing left. Now the x direction, so F1x, we're going to play the cosine game. We can say the x is going to be 17 times the cosine of 15 degrees. And F2x, older brother, would be 21 cosine of 12 degrees. Let's figure out what these are. 16.4 in my calculator. And 20.5 for these. These are the newtons. So the total net forces, let's add them all up. The total x1 would be, I get 36.9, and this is all in the same direction, right? This is all to the east. And here we're going to have 1.9 to the north. Now what am I doing here? This is quite important. This is 1.9 newtons to the north because I subtracted these two. This is negative because it's south. So I added them, but I made that in negative numbers. So now we can basically play Pythagorean Theorem, right? So to the east, the force is this way, and to the north, it's a little bit. So this is 36.9, and this is 1.9. So the total net force is adding these two vectors, and I use Pythagorean Theorem to solve that. I get the net force to be equal to 36.95. It's not much difference because it's such a little bit to the north, right? Newtons. And then we could figure out what that angle is. So the opposite over the adjacent, so the inverse tan, right? I can say tan theta equals 1.9 over 36.9, and this is at 2.94 degrees. So this is the net force, so we found the net force, that's the first question, and the acceleration, assuming no friction on the ice. And so then I can say the acceleration, over here, is equal to the net force divided by the mass, and that's going to be 36.95 divided by the mass, which was up here 19, and this is newtons, and I get A to be equal to, this is vectorially, I would say 1.95 meters per second squared. Now we need to give the direction, right? And we'd say, let's just say 2.9 degrees north of east. So that's the acceleration. Well, folks, it's really about adding vectors if you do, and so don't get overly complex about these kinds of things, but the key thing to understand is that in Newton's second law is that big things accelerate slowly given the same force, and small things accelerate less, and also the degree that you add the force, the degree that you get more acceleration, more mass. Newton's second law, it's not so hard because Houston, this ain't a problem. We'll see you guys in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.